My name is Sami Bengio, and I'm the session chair for the first session today. Thank you, Jean-François. We are going to have first a keynote speaker and followed by two regular talks. The keynote speaker is for 45 minutes and then two 15-minute talks. So first, let me start by introducing our first keynote speaker, Anca, who is a faculty at Berkeley for the last 4 or 5 years. Before that, she was at CMU. And her interest is, as you will see, about trying to work with robots and having them interact with real humans, which, as you might imagine, is not an easy task because both humans and robots are difficult to work with. So the two together is even worse. So with that, let's introduce Anca. And
thank you. This is good. Hi, everyone. Pleasure to be here. So, like Sami said, I work with a lot of different kinds of robots. Mobile robots, quad rotors, robot arms that try to we think a lot about how, given some objective function that the robot has, how do you get them to not just optimize that in isolation, but actually start collaborating and coordinating with humans. And what I wanted to talk about today is what I found to be a major bottleneck in making these robots work. I mean, one major bottleneck is, of course, that people are difficult to deal with. But there's a second one, which is whenever you want to do something like this, you have to start by specifying some objective function, some reward function that you want your robot to be able to optimize. And so let me share what I have to put up with if when I started working on autonomous cars and I had to set up some objective function for the autonomous car. Let me share sort of what happened. So here's an autonomous car. The first thing that happens is that it has some sort of route that it needs to follow. And so we thought, OK, well, part of the objective is to incentivize the car to make progress along that route. That's pretty clear. So here, we want it to go into the left lane and take a left. Then there's rules that the government makes up, right? So you have to stay on the road, you have to stop for red lights and so on. So part of the objective has to include some of that. And then you're not alone on the road. There are other cars around, there's pedestrians and so on. So part of the objective is safety-related things like staying away from these other vehicles. So this was the starting point. Right, so we came up with this simple combination of safety, efficiency, and abiding by the law. And we thought we were done, because what else is there than making progress along your route, getting to your destination safely, and not breaking the law? And it turns out we weren't quite right. But first, let me share the things that you can do even with this kind of reward function. So in this situation where the car is up ahead of, say, a human-driven vehicle, it decides that the optimal thing to do is to start going into the left lane and let the person go through unbothered, which is good. That's what we want. If the car starts behind the person, then it figures out correctly that it should probably brake, slow down, merge behind the person, let the person go first. So it takes a hidden efficiency in order to actually make sure that it stays safe. So that's good. Now, what happens if the car is somewhere in between? Well, in this situation, it actually decides that it's still a good idea to merge behind the person, expecting that the person can actually slow down a little bit and make space for the car. I'm brushing over a lot of details here. It was about one PhD thesis to actually get cars to realize that they can actually influence the actions that other people have, but that's not today's talk. So with this, right, when you design reward functions, you come up with something, you test it in a bunch of situations, and then you declare success. You say, OK, it's doing the right thing in all of these different scenarios, in all of these different initial conditions. That's great. And then, one day, surely, a student knocks on my door and says, oh, here's what the car did in this weird edge case. So this is an edge case in that the car starts kind of not in front of the person, but not behind either. The speeds are matched just right. And so what does it decide is the optimal thing to do? Cut the person off, force them to brake at 5 meters per second squared, because that is a little bit better for its efficiency. And that's not what we want. And so what do you do at this point? You kind of go back to the drawing board. You think about combining these different things differently. In our case, we also decided that we want our car to not be a jerk to other people. And so we should probably speak about that in the objective, in the reward function. So we added this courtesy term, right, that makes the car care about not just its own efficiency, but the efficiency of other people around, so that it doesn't do stuff like make them decelerate at 5 meters per second squared. And then we put too much weight on this term. And so then at a four-way stop, what happens is the car doesn't go, doesn't just wait and let the person go, but instead it decides the optimal thing to do is to inch backwards from the intersection to incentivize the person to go through the intersection faster. I've never seen a human do that. Surprisingly, in user studies, people actually did go faster through the intersection. So that wasn't a problem. But there is a problem, though, which is if you have a car in the back or if you have a passenger riding in your car, they're now freaking out wondering why the heck is the car going backwards, right? So it's not just safety and efficiency and law abidance and courtesy. It's probably stuff like comfort. It's probably stuff like how intent expressive you are, and so on and so forth. And it seems like a never-ending list of things and a never-ending way to tune all these different possible trade-offs. And so I'm very frustrated because we've been working on AI, and now we don't have to specify behavior. I don't have to tell the car what to do at every point. But here I am spending a ton of time specifying reward functions. And this is not a thing just for robots and robots that interact with people. Here's an example that I really like from OpenAI. This is a boat racing game. And this is a DeepRL agent trained to race in the game, which you wouldn't be able to tell if you just looked at it because it's not doing a great job racing. And so you might think, well, there's a bug here somewhere. It turns out, no, the boat is actually a freaking genius. So what it figured out to do is do this loopity thing and hit those turbo boosters the moment they sprung up. Every time you hit a turbo booster, it gives you a bazillion points. And so the boat is basically like, look at these other losers. They're winning. They're trying to win, racing along. I'm just here doing my loopity thing, getting a ton more points. Because reward was points in the game, wasn't, try to actually win. So this sort of thing happens all the time. I'm almost done complaining, but one last thing is that the thing about these robots is once they have a reward function and they're deployed, man, are they stubborn about actually optimizing that reward function. So here's a version of this. I have an arm. It does some motion planning to carry a mug from a start to a goal location, tries to avoid obstacles, the table, and so on. Now, I look at this arm, and I say, you're carrying that mug very high up. And I'm worried because if you drop it, it might break. So what do? I go in and I correct it. I give it a correction. I push on it and bring it closer to the table, expecting that it could then continue to keep the thing closer to the table. What does the robot do? Does it keep the thing closer to the table? No. The robot's like, oh my God, that was so suboptimal. I can't believe I had to put up with this. Let me now go back and do the task in the way that actually optimizes the reward function that was specified, which is to make sure I have a nice clearance from the table. So I keep pushing, and it keeps going back, because that's the optimal thing to do. And it's right. It is the optimal thing to do, according to the reward that was specified. So there's stubbornness. And I do want to point out that I work in sequential decision making, but this is not just a problem in sequential decision making, right? Most AI agents work by optimizing for something. And so in supervised learning, if you use training loss, essentially what you're saying to the learner is, look, all mistakes are equal. Accuracy is king. So if you confuse an apple for an orange, that's just as bad as confusing a person for a gorilla. And that's not what you mean, right? What you mean is that actually some mistakes are much a bigger deal than others. And And this should not be surprising. I mean, we have a lot of myths and legends and stories about this notion of be careful what you say you want, be careful what you specify, right? King Midas wished that everything he touched turned into gold, and it turns out that's not what he actually intended. We have stories about genies with wishes going wrong and so on and so forth. So I think the trouble is that we're burying our heads in the sand a little bit. We pretend that AI is, I have an agent, there are states of the world, the agent can take actions, these actions affect these states, and a reward function falls from the sky upon the agent, and the agent's job is to maximize cumulative expected reward. That's what we write in the textbook, that's what I teach my students when I teach Intro to AI. So that's what we pretend AI is. But I think what AI actually is I have an agent, there's states, there's actions, and then there's a person who wants something. And the AI agent is supposed to do what the person wants it to do. So we tend to draw the box conveniently around this part, because that's the easy part, and focus on given a reward, how do you optimize it? But it seems like we should be looking at the whole enchilada. That's the whole system. It's optimized for whatever a person actually wants. So I don't think I should be teaching anymore in Intro to AI that AI is about optimizing expected reward. I think that it should be about optimizing intended reward. It's not about the specified reward. It's about the reward that people actually intend for you to have. And it's about doing that in collaboration and coordination with people, but that's a different talk. So today we're going to talk about making a little bit of progress on this notion of optimizing intended reward. And to do that, we're going to get a little bit more specific. So we're going to take the space of possible reward functions as a parametric space. This could be a deep neural network where states and actions come in and the scalars come out, and theta are the weights in that neural network. It could be just a linear combination of criteria that someone knows are important. It could be anything in between. But the important part here is that the robot doesn't just get to see what theta is, right? Theta is not observable directly. And so the robot has to have some uncertainty over what that theta might be. And it has to try to estimate it. So we're going to hold a belief over theta, and we're going to try to estimate it. And now if you think about what happens when we specify rewards from this lens, essentially, I'm the designer, and I give my best guess of what theta is. So I come up with some theta tilde. As we've seen in all the examples in the beginning, that's not always exactly what I actually want. But in a sense, we're making robots pretend like it is. We're making robots pretend like, OK, I got a theta tilde. That must be the definition of theta. All my belief, all my probability mass goes on that, and everything else is impossible. So in a sense, we're relying a little too much on this specified reward. And then on the other hand, when I do other things like try to correct the robot, we're not updating the belief at all, right? So we're not learning at all from that. So in a sense, I think it makes sense to optimize specified reward. But when you think about it from the lens of optimizing intended reward, what kind of becomes clear is that most agents tend to overlearn from the specified reward. They basically treat it as gospel, and underlearn or not learn at all from all these other sources of information that are there. So we're just leaving information on the table. And it turns out there's a lot of information there. So let me give you a kind of a toy example to kind of convey what type of information we might have. So here's a simple world where there's a start, there's a goal, and there's some, say, water in the middle. And yes, to get an agent to work in such worlds, I could specify a reward function. I could say, look, goal, good, water, bad, don't do that, and let the agent optimize that. I could also, like we've seen, have the agent do its best guess, and then I could intervene as it's about to hit the water and correct its trajectory. That's another thing I can do. I can also do things like demonstrate to the agent, as we call this kinesthetic teaching. It's almost like what you do with babies. You take the robot arm and you kind of guide it along. So you can demonstrate what it should be doing. I could also give it a comparison. So I could say, here are two trajectories that are pretty simple, and the orange one is better than the one that plows through the water. I could do that. I could talk in natural language. I could say, look, you should avoid the water. And then I could do also this this is probably one of my favorite ones. As the agent is going about and about to plow into the water, I could just turn it off or tell it to stop or something like that, right? So what's interesting to me about all of these different sources of human feedback is that, especially with this one, if you look at a person turning you off or sort of making you stop from whatever it is that you're doing. It's a reaction that we have to make sure that the robot doesn't actually fall into the water. But at the same time, as we're doing this, we are communicating a lot more to the robot. We're telling the robot that whatever it was doing was bad, and it was so bad, in fact, that doing nothing is probably better. And so as we act, we end up, on purpose or accidentally, leaking a lot of information about what the intended reward actually is. And the question that we've been studying is essentially, how can the robot make sense of this information? How can the robot extract that information from human behavior of the kinds that we were talking about and use that to update its understanding, to update its belief about the intended reward? And so if you're looking at comparisons, this is probably the easiest thing. So if the person says, here to trajectories, site 1 and site 2, and site 1 is better, they're very directly giving you information about the reward. Because essentially what they're saying is, look, the reward with respect to the kind of ground truth data evaluated on the first trajectory is higher equal than the reward on the second trajectory. That's now a constraint you have on what data is allowed to be. And so you can easily go from a large space of data to a smaller space by applying this constraint. So that's a direct way to work with that information that the person gave you. It's a little more tricky for demonstrations, and we call this inverse reinforcement learning. So for demonstrations, the person doesn't explicitly say, here's a trajectory and it's better than this other trajectory. But what they're doing is they're giving you a demonstrated trajectories and implicitly telling you that that's better than any other thing that they could have demonstrated but didn't, right? So you're getting this multiple comparisons, essentially, a bunch of constraints that all look like, hey, there's this trajectory that I actually showed you, and it's better than all these other trajectories that I could have chosen to demonstrate, but I didn't. So that's how you can capitalize on demonstrations. And the thing to observe here is that both comparisons and demonstrations you can interpret as the person making a rational choice, rational meaning reward maximizing choice, right? From a set of options. That set of options is very explicit in comparisons. Here's one trajectory, here's another one. I'm going to pick the best one. And it's implicit in demonstrations, right? It's here's the demonstrated trajectory, and implicitly I'm choosing it out of a set of all possible trajectories that I could have chosen. Now, when you go into things like the person switching you off or specifying a reward function, it's a little less clear because they're not kind of giving you a trajectory and they're telling you it's better than this other one. So how do you do that? And what we've been noticing is actually that you can look at all of these sources of information and interpret them as the person still making a rational choice, still making a reward maximizing choice from an often implicit set of options. You just have to do a little bit more work. You have to identify the set of options that is implicit, so the things that they could have done but didn't. And you have to be able to translate these options, which are sometimes language or the person turning you off, into something that you can actually evaluate reward on so that you can talk about the person maximizing reward in some sense. So let me give you an example of this. If the person turns you off, what I claim is that they're actually making a choice. They're making the choice to turn you off when they could have done nothing and essentially letting you continue. So they implicitly decided to not let you continue. They decided to turn you off. That's the choice that they made. What we'd love to do is to be able to say, look, the choice that they made, now I have a constraint. It has higher reward than the choice they didn't make. The problem is, though, that I have a bit of a syntax mismatch here, right? I have a type error, because these are things like language or reward functions or the person turning you off. These are the kind of options that we're talking about, the choices that we're talking about. And you can't directly evaluate reward on them because they're not robot actions as part of the MDP that you define. And so you need a translation piece. You need a grounding function that can take these options and actually map them to actions, to trajectories that you can actually evaluate reward. And so what are those? It turns out you can come up with such a grounding for an impressive number of sources. So if the person is switching you off, really what they're saying is that can get grounded into this trajectory where you're following along what you were doing, and then you get switched off, and you take the non-action, and you keep doing that for a while. And so when they're turning you off, the person is saying, look, that thing, that trajectory that goes up to the water and just stops and does nothing for the rest of the time horizon is better than the trajectory corresponding to the person not having intervened, having done nothing. What does that correspond to? Well, it just corresponds to the robot going about its business and executing the trajectory it was planning to execute, right? So that's how we can get an actual constraint out of this person turning you off. Yes, they turned you off, but that's how you can realize that, look, that means that the reward of the trajectory corresponding to that is actually better than the reward of the other thing that they could have done and didn't. The same thing kind of holds for the person actually specifying a reward function. So if the person specifies a reward function, they're making a choice. What are the implicit choices? Well, other reward functions that they could have specified but didn't. So in my example with the car, I looked at these 3 environments. I tuned some trade-offs until the car did what I wanted on those 3 environments. I could have specified a bunch of other trade-offs. I didn't. I specified those. How do we ground rewards? Because I can't just evaluate the reward R theta of a specified reward. Well, rewards get grounded to the trajectory in the environments that the person actually tested, actually looked at, that maximize the specified reward. This should be a theta. This is theta, that's theta. They could be both theta tilde or theta hat or some other one. And so really when the person is designing a reward function, what they're telling us is that the behavior that reward function is producing in the environments that they've actually looked at, not all possible environments for infinity, eternity, the behavior in the environments that they actually looked at, that behavior is better than other behaviors that correspond to optimizing other reward functions in those same environments. So that's a way to kind of bring everything in the context of what the person actually saw and not assume that the thing that they gave you generalizes to everything else. Good, so just a bit more detail here. The way you can actually think about this as a belief update is in this very strict case where you're assuming that the person is giving you the option that has the best reward, then you're essentially going to be eliminating from your space everything that doesn't satisfy that constraint. In practice, people aren't perfect. They don't just pick the option that has the best reward with respect to their intended reward. And so what we tend to use is this Boltzmann model where, or you might have seen it as a softmax distribution, right? So you can say, look, the probability that the person chooses something is higher when that thing has higher reward, but it doesn't have to always be the thing that has the highest reward. And we like this distribution because it's the entropy maximizing distribution. If all you know about the person is that they're epsilon optimal and you don't want to assume anything else, then this is the distribution to use. A bit more detail, you don't have to ground to trajectories. You can ground to single actions. That just means you have to look at Q values instead of rewards along a trajectory. And you can ground to probability distributions over trajectories. And that means you're looking at expected rewards. So different situations demand sort of different grounding functions. But let me share a little bit about what happens when you actually do this. So here on the top row, we have a bunch of different possible feedback types, like proxy rewards and corrections and so on, in our little toy example. And here we have in orange the choice that the person actually made, relative to the things that they could have done but didn't. So with comparisons, it's very explicit. With demonstrations, in gray, you see, well, these are all the other possible trajectories that didn't get picked. With corrections, we don't get trajectories. When the person corrects you, they're applying a force. They're applying really with arms some torque in some direction, right? And you can think of it as, well, they could have pulled the robot in many other directions with higher magnitude or lower magnitude. All of these are options that they could have taken but decided not to, and so on and so forth. And here with proxy rewards, here's a reward vector that I specified, and it tells the robot that water's bad and reaching the goal is good out of a space of all possible unit norm rewards that I could have specified. Now, when you ground these things, it's trivial for the ones that are explicit trajectories. The grounding is just the identity. We've talked about the grounding for something like stop, right? If I stop, I follow along that trajectory and then take the null action. If you say something like avoid water, that grounds to all the trajectories that actually avoid the water. If you say here's a specified reward, that grounds to all trajectories that are optimal with respect to that reward function that I specified. It could be one, or there could be multiple trajectories that are actually optimal. And then finally, let's take a look at what this does to the robot's belief, which I find really fascinating. So here's, in this little example, there's these two possible things that could matter. And this is the unit circle. And the robot starts off by thinking that everything is possible. If I get a comparison, that cuts my space in half, right? Because for linear rewards, essentially comparisons provide this hyperplane where they say, on the left, on the one side of this, all rewards satisfy the constraint. On the other side, all rewards don't satisfy the constraint, and I'm going to get rid of them. And in particular, for that comparison, what we're seeing is that it informs the robot that water is bad. All the rewards are here, provide negative weight on the water. And we haven't learned anything about reaching the goal or not, because both of those things actually reach the goal. And the one that was chosen reaches it later. Demonstrations are more informative. They cut down the space of rewards much more. What I find kind of fascinating is that if I specify a reward function, so actually give some weights to the water and the goal, if I ground it to, OK, all I know is that these, whatever the reward function is, these trajectories have to be optimal, I'm not recovering a single reward function, right? There are multiple reward functions that produce that trajectory. In general, they're going to be, in different environments, multiple reward functions that agree to the one that you specified. And that's kind of key, because instead of putting all probability mass on the thing that the person specified, you now understand that they could have intended a number of different options. And so what are some implications of doing this? Well, talking about these proxy rewards, here's an example that I like with, again, an arm moving about. And the arm cares about essentially distances to all these different things. It cares about avoiding the table. It cares about protecting the vase because it's fragile. It cares about keeping safe distances away from the person, maybe differently from the person's head, because you're pretty uncomfortable if a robot arm goes near your head. You're more comfortable if it goes near your shoulder, and so on and so forth. So what do we do? Well, traditionally, we look at a bunch of environments and specify a reward function that seems to produce the behavior that we want. And let's call that theta tilde. So nominally, we check that this produces good behavior in a number of cases, and then we're happy, just like with the cars. In this new situation, this is kind of an edge case. I can't even tell you why it's an edge case, but it is. And it happens to be that the optimal thing to do, according to the thing that we specified that worked well in all these other environments, is to plow through the vase. And I don't know why, but that's what's optimal, apparently. So if you instead go back to these environments where the person actually specified the reward for, and you do this belief update trick where you now figure out that there's a space of possible reward functions that agree with this, and you plan an expectation with that belief, then you end up sort of hedging your bets more. And we see consistently good behavior across a number of these new environments. And so the point is that if you don't just say that the reward function is equal to the reward function that was specified, and instead treated really as evidence about the underlying true reward, right? You're going to not overlearn from that. You're going to learn just the right amount, and it seems like having this belief is actually useful in new situations. With the corrections, again, I push on the robot does a belief update, and lo and behold, it keeps the cup closer to the table. Yay. Yay. Another implication is that you can combine different sources, so you don't have to learn just from demonstrations or just from corrections or just from a specified reward. I can specify a reward for you, then I can give you corrections along the way, and then I can give you some comparisons. And every time you do something like this, the robot is going to read into it, right? It's going to treat it as evidence in a Bayesian sense about the underlying thing that you actually intend for the robot to optimize. You could also not just rely on the person to give you all of this. You could do active learning and take matters into your own hands, right? So you could do something where you can wonder what kind, there's many kinds of feedback that I could ask for. What kind of what query should I make that in expectation maximizes information gain? And so we do this for cars, for instance, and the car says, well, here's the situation. Should I cut the person off, or should I merge behind them? And you say, well, you should merge behind them, and that gives the robot evidence about what you want. It turns out that doing it actively is important, which is interesting because in a lot of settings that I've tried other than this, doing it actively does not actually make that big of a difference, but there seems to be quite a substantial gap in learning performance if you choose these queries actively. And we also see benefits of combining these different types of feedback. So we see that if you just rely on demonstrations, at some point you cap off. And the reason you cap off in your regret is that on new environments is that essentially demonstrations only tell you that the best thing to do is better than everything else. They don't tell you what happens in the null space of that. So how do two suboptimal things behave? And you need to know that because you're going to encounter new environments in which that difference between a reward function that thinks that A is better than B versus one that thinks that B is better than A actually produce different optimal behavior at test time. And so that's where we see this tapering off. Comparisons don't suffer from this because you can eventually get to the correct thing. It's just much slower. And if you let the robot actively decide which one to query for, you see that you can drop in regret much quicker. One of the coolest things is that once you adopt this lens that everything that people do is a approximately reward rational choice from some implicit set of options, you realize that when they decide to give you some feedback, when they decide to say, turn you off, that is also this meta choice that they made. They had other kinds of feedback available to them, but they chose to not give you that kind of feedback and instead tell you to stop. So in this little example, if here the water or the lava is over here, so basically I can tell the robot to stop, and the robot interprets that in the naive way that we've talked about and makes some belief update. Instead, the robot could also realize that the person could have provided a correction to its trajectory, but decided not to. Instead, decided to tell the robot to stop. And the fact that they decided not to means something. It means that probably corrections weren't as appropriate for this task compared to telling it to stop. And that way, you can infer much more and cut your belief space and focus the probability mass on the correct hypothesis much better. So this is kind of this meta reasoning level of there are many types of feedback. Now that I get to combine them, I also get to reason about the type of feedback itself as being a choice that the person made, and I should be able to learn from that. And so here's a laundry list of a bunch of different types of feedback with their corresponding set of options and their corresponding grounding function. This is just to show that there's so many possible sources, and you can interpret all of them in a sort of consistent way. And now in the last 5 or so minutes, I want to share probably my favorite kind of feedback, my favorite source. And it's a little bit like this. Imagine you walk into a room. You're a robot. No, you're not a robot. Let's say you walk into a room, and someone tells you, clean it up. And there's many things in the room, and there's also this huge house of cards. probably, despite the fact that the person did not tell you to not destroy their house of cards, to not clean that up, chances are you wouldn't destroy the house of cards. You would clean around it and leave the house of cards there. I bet that every single one of you would leave the house of cards untouched. And so what's up with that? How can we get robots to figure this sort of thing out, right? There's no behavior. They didn't see any behavior. They just got this thing, which is like, OK, walk in, clean it up. So far, what I shared with you is a lot of different sources of information that are all about behavior. So if a robot is in a room with a vase, in order for it to figure out to not break the vase, that the vase is somehow important, it needs to actually see behavior. Like it needs to get stopped as it's about to go for the vase, or it needs to see a person going out of their way, avoiding the vase, and then they can read into that behavior and say, oh, the vase must be important, got it, right? That's what we've talked about so far. But presumably, if you walk into a room and there's a vase that's just there, even if you haven't seen what the person has been doing, you should still be able to figure out that the vase is important because it's there. No one knocked it over. It's not easy. It's not trivial to knock over vases, and yet the vase is there. So what's up with that? And so the interesting thing is that because people have been acting in this environment, even the state of the environment, without seeing any behavior from them at all, gives the robot information, leaks information about what people want, leaks information about the intended reward that is completely untapped right now. So when an agent is deployed in an environment that the human has been acting in, there's information in that environment. And how can you capitalize on that information? Reward rational implicit choice. So it's the same thing all over again. The person, except now you can think of the state of the environment as a choice that was made. You didn't see the behavior, but you see the state. What are the implicit options? Well, other states that the environment could have been in, but is not in. It's in this state. How do you ground a state? Well, you ground it into the possible behaviors that you haven't seen, but that the person could have done in order to enter that state from a distribution over initial states. That could be uniform, or you might know something. So that's how you ground this. There's a different, I'm going to skip this. There's an almost equivalent way that's also useful. But essentially what this boils down to is you're in a room, and the robot is thinking, OK, I didn't see what the person did, but what would they have done if they wanted to break the vase, if that was what they cared about? Well, they would have gone through and broken the vase. Is that consistent with what I'm seeing? No, the vase is intact, so that could not have been the reward function. What if they didn't care about the vase? Well, they would be efficient. They would just go through and break the vase, so that's not consistent. What if they actually wanted to not break the vase? Well, I didn't see what they actually did, but they would have gone around, and this is the only thing that's actually consistent with the state that I'm seeing. So that's essentially what's going on in the robot's head. So that means that you enter a room, the person tells you to go to the purple door, and you do this, and you actually go around the vase because you ran this inference. Or kind of a cute example is this was an undesirable, breaking the vase was an undesirable side effect that was avoided. There are some desirable side effects that the robot can infer too. So here's a cute example that my student Rohan came up with. You're in this room where there's a train running, like a battery, one of these toy battery trains. And the person tells you to go to the purple door, but the robot figures out that the train is running, which means that someone cared about actually keeping on giving batteries to this train so that it keeps running. And so instead of just going to the purple door, the robot goes, grabs a battery because the train is about to run out, puts the battery in the train, and then goes to the purple door, which I thought was really cute. I mean, this kind of stands for there are things that we care about, like if all the shoes are aligned, right? That we took effort to do, and so the robot will now know that that's something that we care about. And when I leave and no longer align the shoes in a row, the robot might actually know that, look, this is something humans care about, maybe I should help with that. So that's kind of where we want it to be, and then the train keeps running. Good, so essentially I think that we humans can't help but leak information about our intentions, about what we want. And it's high time for robots to be able to capitalize on all that leakage in order to try to optimize what we want as opposed to what we necessarily specify. If we think of all these sources as being through the lens of they are choices that people make from some implicit set of choices, then that tends to prevent over-learning from specified rewards and under-learning from a lot of other information and kind of preventing robots from just leaving that information on the table. In terms of what's really hard still, I don't know how to decide on a space. I said in the beginning, look, let's say that rewards lie in some parametric space. What should that parametric space be? And in particular, what should its capacity be? The challenge is that if you look at linear combination of features you already know about, you're going to miss out on the fact that it's possible that people care about stuff that's not in that space. If you say it's a giant neural net, then it's going to take you a lot of human feedback in order to narrow down on what the actual intended reward is. So the sample complexity of that is going to be huge, and that's a problem. And so you kind of want to go in the middle somehow, but how are you going to go in the middle? How are you going to make assumptions that are correct? What's the right inductive bias for reward functions? I have no idea. Of course, the moment you acknowledge that people are making choices from implicit sets, you could be wrong about that implicit set. And maybe the most obvious point is when I was talking about, look, the person decided to stop you, and so that means that they decided to not give you a correction. I don't know, maybe they didn't think about it. What if it's not part of the actual reasoning that they did? What if they didn't realize that you could do a correction? So you could be wrong about that. And then finally, we kind of talk about people as being, first as being reward rational. They pick the option that's best with respect to the reward. And then we relaxed that a little bit and said, look, you can account for some noise. People are not always going to give you the best option. It turns out that that noise, this maximum entropy model, is highly wrong in many places. People are not just noisy, they're systematically noisy. They have systematic biases. And so you give them something that's a clickbait versus something that's actually informative, they're going to go with the clickbait, even though that's not the right thing. That's not what they actually, that does not optimize what they intend. But they're going to do it anyway. You give them a cookie versus an apple. They want to be healthy, but they're not going to think long term. They're going to take the cookie, right? So people have these systematic biases, and the trouble is that if you don't know about them and just assume that they're approximately optimal, you have huge losses in your accuracy of inferring the reward. So if you look at their behavior and say it's optimal and try to figure out their preferences from that, it turns out you're going to be very, very wrong, and that's a big issue. So to wrap up, because Sammy's going to kick me off the stage, I think we've been getting these agents to bury their heads in the sand and ignore this part because it's a complicated part. This notion that there's a human that has intentions is just really, really tricky. And it's more convenient to focus on optimization. But optimization is half of the story. The other half is let's figure out what people actually want us to optimize in the first place. And that's what we've been doing a lot lately. I've done none of this. Everything was done by these amazing students, and they deserve all the credit. So thank you very much for listening.
Thank you, Anca. We have time for a few questions. So I think there are some mics left and right. Please come to the mic and ask questions. Craig. Try again. Yeah.
Oh, OK. Oh, yeah. Thanks for the very nice talk. I think these are really important topics that don't get enough attention in the AI community. Just one specific question. A lot of the forms of feedback that you're looking at in these situations kind of assume that this human feedback provider in some sense is hyper-rational. So they know what a good behavior is for this agent that they might have no idea what their capabilities are. And in general, one of the reasons we want AI is to get things to do things that we can't really do well for ourselves. How would you try to incorporate human feedback in those situations? I mean, obviously, it's trajectory comparisons, if framed in the right way, are okay. But critiquing behavior is, I think, a little more problematic in those situations. Any thoughts?
Yeah, good point. Yeah, like you said, comparisons are the cop-out answer to this because people can recognize the behavior that's better even if they can't produce it. I think the real answer is to go in the very end of the talk when I mentioned, look, there's actual systematic irrationalities that people have because they can't actually compute the optimal thing. And so I think taking those into account is really important. And one thing that we've been playing around with is just looking at the Bellman update and basically breaking it in all sorts of ways to account for possible suboptimalities that people might have. Like, the transition function might be wrong and so on and so forth. One particularly interesting one, and maybe to this audience, is that we found that people are suboptimal in their choices also because they're still learning about what they want. It's not very clear when, I don't know ahead of time what movies I prefer. I have to watch them in order to actually figure out whether that was a good thing or a bad thing. And so I think that modeling, it turns out to be important to actually model this aspect of people are still learning. Some of their actions might be completely exploratory actions. And if you have robots, agents, that know about this, they can actually help the person and fix their under-exploration, their over-exploration, and so on. If you have robots that just assume that the people are approximately optimal and know what they want already, then you have these huge error bars on what the preference is. Thank you.
One last quick question.
Sure. Thanks for the talk. So, I mean, both your examples where you were sort of pushing down on the robot as well as where you're inferring the state of the room.
Yeah.
So how do you sort of figure out what is the optimal choice to make? It may not always be unique, right, what the human is attempting to do or what you're trying to get it. Is it iterative or how do you sort of map it into something?
How do you figure out what the optimal choice is? So you're going to look at the person and assume that they're going to pick something that's approximately optimal. If you assume that they pick something perfectly optimal, then you're going to put your observation model has uniform distribution over all the optimal things. If you're assuming that usually we assume that they're noisy rational, so the probability of them picking something is sort of proportional to the exp of how good that thing is with respect to their reward. So so it's okay if there are multiple things that are optimal. People are just going to pick one of them. People are probably not going to even pick one of them. They're going to pick something suboptimal, but that's okay because it's part of the noise model.
Okay, but I guess I was trying to ask, like, how do you sort of figure out what the intent was? Like, was it to go closer to the table, or was it like?
Okay, good. So very good clarification point. That's why it's important to have a whole belief as opposed to take a maximum likelihood estimate. So when you take a maximum likelihood estimate, you're going to go with one of these hypotheses, and you're going to say, well, maybe it was closer to the table, or maybe you're going to converge to something else. When you have a belief, you're like, there are multiple things that explain what the person just did as being an optimal thing to do. We found it's very important to somehow approximate that full belief, which is a pain in the butt, right? But Metropolis, Hastings, et cetera, those are things you can try.
With that, we're going to cut, and let's thank again Anca.
Thank you.